Hello once again. This is Lecture 9B, the second of our lectures on generation with limited energy supply. We've previously covered the scheduling of generators with take-or-pay gas contracts, for example, and with coal, where it's being dropped off at two different power plants, and we saw that using linear programming we can schedule the coal deliveries in a way to minimize the operation of the overall power system over a long period of time. Today we're going to talk about the hydrothermal scheduling, so we go back to this same intro slide here, only this time we're talking again about water coming in to a reservoir. If you fill the reservoir too much, it spills. You have to provide for spill, because if you don't, the water is going to find some way to get around the dam. It's going to leak around, and what you don't want it to do is to get into the earth and rocks that are holding the sides of the dam and erode them away, and then basically can cause the dam to fail. So you want to have a controlled way. We draw it here as being over the top. It's often the way it's done, although often the spillway is a constructed pathway that they build around the dam. Instead of over the top, it'll go around the side, but it's been constructed with cement, and it's enforced and so forth, so that if the water gets too high, then there's a path for the water to get downhill so that it won't wreck the dam. You don't want it to ruin the impoundment here, the structure. Q is the water that comes through the turbines, and there can be multiple hydroturbines. We have not in this particular chapter dealt with the fact that hydroturbines have a unit commitment type problem. And if you do have a hydro unit commitment problem, then oftentimes people go to Lagrange relaxation to solve the hydro problems, because they're doing on and off scheduling. Okay, and these plants here, we represent the output of this. All of the spill and all of the Q goes into the reservoir at a lower level along the river, and then the same thing down here until it gets discharged finally into the lowest level of the river, which eventually will run into the ocean. Okay, now here's a little bit more detailed diagram of a hydro plant. We have the forebay, the afterbay. So this is the forebay. This is the depth of the forebay. This is the water that's been impounded. This is our reservoir back this way, and that can go back for miles and miles. If you look at pictures of the some of the big hydro plants, for example, in the U.S., if you look at the Glen Canyon Dam and on the Colorado River, the reservoir goes back for many miles. Here's the afterbay. Drawn here is much lower, and the energy comes from letting water fall. Okay, the same principle as was used by early people running grist mills and sawmills, where they let the water fall onto a wooden wheel, and then the weight of the water turned the wheel. Well, here the weight of the water falling goes into, this is the turbine, and the turbine spins. Notice that this particular one that we've drawn, it spins, and the water here is going in here and then down here out this so-called draft tube into the afterbay. It spins. Now, it doesn't spin anywhere near as fast as you do for a steam electric unit or one that's like a combined cycle unit where it's gas turbines. It's spinning much slower, so they'll have many more poles, so that they can still deliver 60 hertz electric energy from these generators, but they are spinning much slower. But they are taking on a huge amount of water coming down this so-called penstock. That's the path the water takes. Up here, we at the intake there may be a valve up here, and there are, we call them trash racks, just something to filter out sticks and twigs and leaves and junk that may get in here. That actually, the trash racks have to be cleaned periodically to keep the water flow coming into the turbine. If the forebay gets too low, if the level of the water is down here someplace like this, well, you can't generate anymore. So, and as the forebay level comes down, the water falls through less and less distance. You get a little bit of less output. Down here is some pictures of some 4 different generating units, and here's the incremental water rate. Now, what we do for in the U.S. is we take an amount of water that's 1 acre by 1 acre. Okay, an acre is 200 feet by 200 feet, and 1 foot deep. That's a big block of water. It's a big, huge chunk of water. And this is 1 acre 1 acre foot. And it's 1 acre on the top by 1 foot over here. Okay. In many other countries they use 1,000 cubic meters or something like that. This is just a common way that it was first done, and it became. Notice that the incremental water rate. Here's this is P down here, and this is what we call Q. Now, actually, this is the incremental water rate of acre feet. This is Q. Pardon me. This is really dQ over dP over here. And the incremental water rate is fairly flat until it reaches a certain point. And what it really says is that the characteristic of Q versus P is linear until you're pushing so much water through that you begin to get turbulence, and that turbulence effect causes this curve to come up like this. And now the thing is becoming less and less efficient, and you notice that once you start hitting this, it takes more and more and more acre feet to get 1 megawatt hour. Okay, acre feet per megawatt hour goes way up. So you'd like to operate down in this flat region for the hydro turbine. We talk about the time intervals. Again, J, we don't use 1 hour. We can use 2 or 4 or 6, any number of hours per time interval. R is the inflow. This is a river, and we're just going to assume that, well, we could schedule that. We could give you a schedule of inflow. For a river, it may more likely be constant over several days or weeks, depending on what time of year. V is the volume in the reservoir. Q is the discharge, or the water coming out of the hydroturbine. S is the spill. And so here's this is the problem for hydro scheduling. I've got a load for each hour J. I've got a hydro plant P of H, and I've got a steam plant P of S, and they're always on for the time periods that we're dealing with. And the idea is to minimize the cost of operation of this one by adjusting how we operate the hydro plant. So we don't have a cost. There's no dollar cost for the water. Water comes literally from heaven. It comes into the to the plant, and pay for it. Don't get me wrong. We pay for the capital cost to build this, but once it's built, we don't pay for the water coming into it. Whereas we do pay for that fuel. So let's minimize the amount of fuel to supply this load by adjusting the hydro schedule. Here's the mathematical statement. Minimize overall the steam units, NJ times F of J for each time period. We have a in this case, it's very similar to the gas contract. We're going to have a Q, and we're going to say, I'm going to burn so much water discharge over the whole period. I have so much load. There's my loading, says the load minus the hydro minus the steam, where N is the length of the jth interval. The sum of all the N's is T max, so that's the total time that we're adding up. The hydro plant has a starting volume and an ending volume, and there are flow limits as well, the Q. There are Q limits on the hydro plant. I cannot dump too much water down the river, again, because of government edict that says the flow has to be limited so that, let's say, pleasure boats don't get tipped over in the water, or that the eddy currents and turbulence in the water is such that it erodes the banks on the sides of the river. So there are Q limits. And then we're going to have a fixed discharge, maybe for each hour if you want. Loads are constant in each interval. So here's my Lagrangian. Here's the sum of the steam units, and I have a loading constraint. These are summed over 1 to J max. As with the gas plant example, I have a lambda for each J, and then I have a gamma, just like I did with the gas plant. And here's the discharge. The total discharge is a function of each hourly discharge summed up. I take the derivatives with respect to the steam plant. Now, if I have electrical losses, that I get this term. We put that in there because with hydro systems, they're apt to be spread way out across the countryside, and so then transmission losses become significant. Okay, so these are just the economic dispatch equations, and here we have our gamma, our fuel price, and what is it? It's a water price. So the way, if you go through all the units here, this is dollars per megawatt hour. This thing comes out to be dollars per acre feet. It's a false price that we put on the water so that we can do the scheduling. And as we did with the gas, we can do it here. We can select the gamma, and we can set this up initially, do a lambda dispatch for every hour, find the Q, and at the very end see if we've met our hydro constraint. Now, part of the reason we have this extra loop in here is because these losses are going to change. But in any event, you schedule this the same way, and then we project a new value of gamma. So it's the same kind of adjusting of the water worth function. Now that works if you have one hydro plant and a steam or a group of steam plants. If you have this, if you have 3 hydro plants in series, you have 3 constraints, which are the volume continuity. It says the volume in 1 at J is equal to the volume at J minus 1 plus the inflow minus the spill and the discharge times the number of hours per period. Same thing for 2, except 2 has an extra input. 2 has the Q in and the Q out. 3 has the Q2 in and the Q3 out. So I can write a Lagrangian this way, but now I have 3 different values of gamma. Now you have got into a situation where it's basically impossible, not impossible, but very, very difficult to solve this problem where you keep to these volume constraints. and optimize and finding three different numbers here, which will minimize this function, is extremely hard, and it's not the way to do the problem. It's not the way to do the problem. We're going to come back to solutions that to show you how they work, but I wanted to talk about a different way of doing this. We showed you this way back in the beginning of the introductory slides. Pumped hydro. Now, pumped hydro says that I have a river here. Here's my river, and I have a mountain. Here's the mountain, and I built a power plant on the top, right at the edge of the river here, and I can take water into the plant, and I can pump water up a pipe. And on the top of the mountain, I hollow out another reservoir. So here's my reservoir here up on the top. Here's the reservoir at the bottom. So I can pump water up. I can buy electricity, and I can pump. When I want, later on, I can run the water down, and then it goes through the generator and back into the river, and I can generate. I can pump and I can generate. This is called a pumped storage system. It is one of the few, and I mean one of the few, means of storing electricity. You put electricity in, you move the water up, you move the water down, and you get electricity back. The overall efficiency of pumping and then generating, you get about 2/3 of the electricity back. Well, you say, boy, I waste 2/3 of the energy. Well, it turns out that there are some there are tremendous advantages, and you can store huge amounts of electric power, hundreds or thousands of megawatt hours in these facilities. The only other large-scale storage means that we have is to take we talked about this before, is to take and buy electricity and compress air and put it down into an underground facility. Now, you can do that with natural gas, or you can just do it with air, and then you let the air come back up, and it just goes back through a turbine, and it generates electricity coming back up. And those have been built where possible. For both the compressed air and pump storage, you need special, topographical facilities. You need a mountain next to a river, next to a lake. And you need to be able to get permission to build this plant and build this reservoir up here. Okay, so here's the way that we analyze this. Here is the cost of operating the power system, and we say this by the way should be dollars per hour over here, and we say that cost at a low value has a low slope. As we get way up on the steam units and we get less and less and less efficient steam units, this thing gets to be very steep. So let's say that I buy this much energy. I buy energy by asking the steam system, the steam plant or plants, to increase their output by that much, and the added cost goes up by that much. Later on, that would have been done during the let's say the nighttime hours when the load was low. Then when the load was high during the day, I ran the pump storage as a generator, and I generated back the exact same amount. Now I can generate the same megawatts, but I don't get the same megawatt hours, but just the same by generating the megawatts. Because this curve is steep, I get a savings that's that big. And the difference between this cost and this savings is a significant number. So there is a savings. You basically, it's like playing the stock market. People buy low, sell high. Buy when the incremental cost of energy is low, and then sell when the incremental cost is high. And the differences results in a significant profit, if you will. And so we drew a load curve like this, and we said this is on this curve, this is load going out this way. And when the generation is at its peak, we're going to generate. When the load is at its peak, we're going to generate, and when the load is down here at the a low value and energy is cheap, we're going to buy energy and store it. So you're buying and storing, and then you're generating at the peak. And the overall cycle efficiency, as we said, is 2/3. Here we go. Here's this picture of a pump storage, and this is the pump, and this is the generate. Here's G, and this is P. And as I say again, you need a reservoir, you need a mountain. Not too difficult to get. It's much more difficult to convince people that building one of these is environmentally benign and so forth. And there has been a lot of opposition at times, but they have built many of these around the world. So we have two plants. We have a pumped hydro plant and an equivalent steam plant. And we've got our variables over here. We're going to add up all the steam plant costs down here. And during the generate intervals, we're going to supply the load plus losses, and that's going to be offset by the hydro and the steam together. This is steam, this is hydro. And the volume in the reservoir, okay, is actually generating is going in the other direction. So the way we did this equation, you would really swing all of these over to the other side, and it would say VK is VK minus 1 plus R, water coming in, minus Q. But this is the way the equation comes out. And it simply means that the volume of the water is going down. Now we're gonna build during the generate intervals, we do a Lagrange equation like that, and this is the YK for the generate intervals only. During the pump intervals, we change the sign in front of the hydro, because now I'm supplying load, losses, and I'm putting power into the pumping. And in this case, the volume in the reservoir is going up. So this is now got a minus sign, and I have a Lagrangian with lambdas and with gammas on the pumping intervals. We do the same thing that we've always done. We take and add them all up, and here we've got some Lagrange multipliers that talk about the initial and the final volumes. And here's our Lagrange function. Start taking derivatives. This is the common way that we take derivatives during the generate intervals and during the pump intervals, where we get a change in sign right here, and we set these various derivatives equal to 0. Now, pardon me, and you can set this up and you can solve it and come up with the optimal. What you're looking for really is the optimal amount that you're generating, the optimal amount that you're pumping across all those intervals to meet your volume constraints and so on and so forth. So you can do that simple scheduling that way. And so now we're gonna go back to hydro scheduling. We're going to talk about hydro scheduling using linear programming again. Here are all the variables. steam plant, hydro plant, turbine discharge, spill, volume, R, inflow, slope of piecewise linear steam plant function, slope of the piecewise hydro turbine function, slopes of the linear spill function. We'll show you that function in a minute, and electrical load. So we have to basically take our F function, which is nice non-linear function, and make it into linear segments. And the more segments that you allow, the more accurate it portrays the nonlinear function. And we did this in chapter 3. We could do just economic dispatch, so it's the same breakdown that we did in chapter 3 for a steam plant. Here's the hydro plant that goes up, and then it may come over, or in fact it may curve off this way. But you've got to have linear functions like this to represent the hydro plant. And here's the spill. The spill is actually 0 up to this point, and then it spills, and then there's a nonlinear equation for the spill of a hydro plant. And we add all these functions. They're now all linear. We have volume constraints. We have loading constraints. The LP for one steam and one hydro plant requires 8 constraints for each time step. That's amazing. 2 constraints for the steam plant, 2 constraints for the hydro turbine characteristic, 2 constraints for the spill characteristic, 1 constraint for the volume continuity constraint per time period, and 1 for the load balance. LPs get to have tens of thousands, if not hundreds of thousands, of equations and variables. They are very sparse, so you have to have very, very special software to handle these ultra-large linear programming solutions. But they're available. Commercial LP codes are available that can easily solve these problems. Last of all, we have dynamic programming as a solution for hydro scheduling. This was, I would say, until very, very large LP codes were available, dynamic programming was the preferred way of doing it. So here we have again the same variables we had in the LP, but now we have a nonlinear function for the cost of the steam plant. Here is it's a quadratic function for the discharge as a function of hydro output, and we have our simple volume, spill, discharge, inflow, hydro plant, steam plant, and load. There's a very nice problem in the textbook that asks you to solve for an optimal operation using dynamic programming. Incidentally, don't try to do that problem by hand. Write a program to do it. If you try to do it by hand, you will spend hours and hours and hours, and you'll make one mistake. I'm just saying what students often have done. It just requires so much calculation that you need to let a computer do it. Okay, so you have a volume continuity constraint. It says that the volume is equal to the volume at the end of the hour is the volume at the beginning of the hour, plus the inflow minus Q minus S times the number of hours in the jth time period. And once again now, what we're doing, the states, okay, here are the states. We have these dots, states. Here are the states. Remember our friends, the dots. Transportation problems, unit commitment problems. States vertically, time or periods horizontally over here. Now here we're going to use 1 hour period. You could have 2 hour periods, in which case we should go to a J. In fact, this should be a J. let's just put J there. And this should be an N sub J. So, states. So, the optimal path is defined by going from a certain storage, is the states are storage volume. So, I'm letting in this case, the path says let the volume fill 2 units, then let it fill 1 unit, then let it fill 1 unit, then don't do anything to the volume, then start to draw the unit down. That's a path that, and this is a different path where we let it fill just 1, then we drew it way down to its minimum, and then we just left it sit there. So a path through these states represents a hydro schedule, and depending on the difference in the volume states, if I know the difference in volume states, then dividing that by n, adding the infill, I know what the Q was. So if I know what the Q was, then I can look through, I can go back through, and then from there I can get the pH for that hour J, and then knowing the load, I know what the PS J was. So there's a schedule. So all I need is the volume changes, the states at each hour, and I can get the Q, from which I can get the hydro, from which I can get the PS. And I can do a hydro schedule this way. And this works very well. It does not work well for multiple units in series, like we showed with the 3 generators, the 3 hydro plants in series. Dynamic programming it's possible to do that, but it's not recommended. Thank you very much.